Right. So I apologize for having to reschedule this lecture. The seminar has been so I know I said I wanted to continue talking about the energy momentum tensor we left off last term, but I changed my mind. Just because I'd like to get a little bit further in the syllabus than I would if I spent a week talking about it. Energy momentum tensor and CNA theorems. Those are all super fun stuff and very interesting and all that. But I want to go a little bit go a little bit further in the lecture in particular, and hoping to kind of get to at least finish constraints on the correlation functions before the end of this at the end of the course. So to that end, I need to talk about a couple of things. One is we need to talk about representation theory of the also. So the next couple of lectures are going to be a little bit algebra. So just I'm assuming that everybody's done at least the course abstract algebra. But if not, Jan van Zel is teaching that course in index. I think all those lectures are going online. Of course, this is the course on the algebras and the representation theory. I recommend you go through those. I also have 700 lecture notes. So we have a slide for pre-IOS. So we would like to take those and Xerox those and upload them. My guess is telling and I'll add it up.
For your episodes, are there any specific sections that are more useful for this?
We're just understanding what representation theory is and how it works. But basically, the representation theory is restricting your attention for groups to matrices, and linear algebra, right? So only linear algebra and any abstract algebra you can. I'm not interested in theorems and stuff, but there's a bunch of things, and actually we've covered all of these things last year, last semester in the different geometries. But if you haven't, again, go through Jaco's notes or the lectures online and see where they're. Okay. So we're going to talk about this. Once we're done with this section, which is a fairly long section, probably take us maybe a week and a half to finish. Where this is going to lead us is it's going to tell us how to organize states within our node space. So it's key. It's going to tell us that all. Okay. Well, the first statement I'm going to make is that conformal field theories are democratic in the sense that no fields in conformal field theories are particularly favored. Right? I'll clarify this in a little bit. But it's going to tell us how to organize these fields in a useful way. Then we're going to spend a chunk of the lectures proving a particular theorem, but it's proving a particularly important result, namely that the conformal dimensions associated to conformal fields are bounded. They're bounded by a set of invariants called Casimir invariants of the theory, which is the algebra theory. You don't really need to know, we'll go from examples and get an idea of what it is. And maybe I'll have you complete it for some particular subject, but it's a computation by the end. This set of lectures are a little bit close to the tracking edge of the field. But there's a lot that's still either freshly proven results in the last 5 years or so, or open questions. And so there's not a lot of, oh well, this is long solved problems still back of the envelope, or here's the back of the tablet problems you got calculated, right? So these are still roughly fresh of the present kind of results that will be talking about. And these are this is the background that we need to develop this. Much of this field is, well, we thought we solved all these problems back in the 70s and 80s, and so it was stagnated for a while, and suddenly, there's been this flourishing set of activities that have happened, and they all kind of go under the guise of a form of bootstrap. And there's been a number of conferences and stuff in the last couple of years on bootstrap, and suddenly we can make all this progress in the form of failure. So that's what that's what we're talking about here. So a lot of these results are new, and what we're trying to do is package them in a way that makes them intuitively clear. And then I'll try and select problems for your exercise that are kind of basic level problems that you handle on what's going on. But keep in mind that a lot of these problems, a lot of these statements that we're making are things that people demonstrated in the last couple of years. So this is not like that's it's right up at the cutting edge of the field. Okay, so the question I want to start asking, and that will motivate us for the next couple of lectures, is how do fields transform under conformal transformation? And we know that in conformal field theory, there's this thing called the operator state correspondence, which tells us that if we're talking about field, a state that live in a space, then we might as well talk about operators that act in that little space as well. They're much more much less in this story, because we showed you in a couple of lectures ago that there's a more or less one-to-one map that allows us to think about one or the other. Okay. So the question is, how do fields, I'll give you some Lagrangian, Hamiltonian, so basic fields, tell you that the theory is conformally invariant. I want to know, how do these fields transform under conformal transformation? I don't know how points, space-time transform, that's what we've been talking about all this time. Now we're going to function of those points in space-time. So how do fields, or alternatively operators, by the operator state correspondence, transform under formal transformation? The point is that conformal field theories are really nice because two things. One is they don't privilege any set of fields, but they help the fact that these fields transform differently under conformal transformation allows us to organize our field in a nice way. We'll end up, I've told you this already, there are these fields called primary conformal fields, right? So primary fields, and then when I act on these fields with various operators, I use descendant fields, right? So these primaries and descendants are fields that transform in particular ways. What we're going to learn here is that they can only transform in these ways. So I'm going to use these transformation properties in the following lectures to write down correlation functions. Not because I've calculated the correlation functions using path integrals or whatever, but because these correlation functions can only look at this. So that's a hell of a rigid constraint to another theory, and it's highly useful. If I can just write down a forward function, I mean, how many of you have the field theory at the same time? No, okay. But I know I see this kind of much else if you have something. But if you do a course of quantum field theory, much of that course is about calculating correlation functions. And what you'll find is that even 2-point correlation functions, these functions of the theory are non-trivial to calculate. And the more non-trivial I make the theory, the more non-trivial these correlation functions are calculated. Today, if you're studying things like quantum chaos, then the computations du jour are 4-point correlation. Right? 2-point correlation functions are 4-point correlation functions. It's really hard. So suddenly, if I come to you and I give you a highly non-trivial theory, like a conformal field theory, and I tell you that all of the correlation functions are heavily constrained, it's not, what it will boil down to is computing some coefficient, because the rest of the properties of this correlation function can only look this way. That's a hell of a simplification to come up with. Right, so that's what we're going to see in the coming lectures. Right. So I hinted at this just now, but let me make this explicit. Unlike usual conventional quantum field theories where there are certain privileged fields. For example, if I'm talking about quantum electrodynamics, right? There are fermion fields and there are gauge fields. These are privileged fields. I write down my Lagrangian in terms of these fields, and I calculate things involving these fields. In a conformal field theory, any local, possibly even composite operator is an interesting operator for us. Not just the fermions, not just the gauge fields. Okay, so in a conformal field, I can consider polynomials in F value or polynomials in size, or even their derivatives, and they're perfectly acceptable operators to study. They give us information about what they're. So, unlike conventional UFPs like QED, privileged fields. Now, for example, QE, some set of fermions, say psi alpha, or the photon A mu, so the fermion fields, photons. In a formal field, any local O is thing. For example, O would be some function of psi alpha, derivative of psi alpha, or even F mu. That should be some polynomial. F. Sorry, so polynomial in these fields. And there will be no trivial information contained in this object. Okay. So this is just an aside point to make about CFTs. But circling back to our question about how operators transform, or fields of operators transform transformations. Let's start off as we've been doing, as usual, with something that we're familiar with, Poincare transformations. Poincare transformations, as we said before, are a subset of conformal transformations. So what we're going to do is explore a little bit of Poincare transformations and Lorentz transformations, and then we'll learn some lessons and see if we can port these lessons to the biggest set of conformal transformations, right? So all the heavy lifting will be done with things that we're familiar with, and then we'll make some observations about our extended full set of conformal. So let's start. Ask, how do fields or operators transform under Poincare transformations? Poincare transformations that we wrote down, which take x mu to say x mu tilde, and x mu tilde would be some element of the Poincare group G, of x, would be some important Yes. Right, so this is some specific element. Under this confirmation, some generic field, and I'm going to write this as phi sub A, because it could be a scalar label, it could be a fermion label, it could be a vector label, it could be some combination of the two. I don't really care at this point. This is just some generic field of material. But this is how this generic field will transform. So under the transformation one, some generic field phi A in our theory will transform. So phi A will go to phi A tilde. Label all of these things just now of x. And phi A tilde of x is A LA B of G phi A of the inverse phi B inverse x. So come back to this. This is a generic field in our theory. This is some labeling properties of this field. It could be a tensor, it could be a spinor, it could be a scalar. I don't really care. At some point, I will care. But what I'm interested in here is how a generic field transforms. A generic field will transform. This guy, LAB. Okay. So there are 2 points to notice. So again, Einstein's summation applies here, and I'm summing of the D's. There are 2 points to note here. This transformation the transformation law comes in 2 parts. Right? The first part is generated by just a single generator of Poincare transformation, this guy G. Here, I have a matrix of generators. Okay, and it's clear that I can factorize the transformation into 2 parts. This part here is called the orbital part of the transformation. And the analogy comes from studying how things transform in quantum mechanics, where I talk about angular momentum, and I will have orbital angular momentum, spin angular momentum, and I'll find that the transformation factorizes in the same way. This is the orbital part. And it's generated by a single generator. And it is the same for all the fields in the theory. So, irrespective of what the field is, what type of field it is, it works the same. So basically, the argument here goes from x to g inverse x. Okay. So this is the orbital part of the transformation, generated by a single generator. And is the same for all fields. Yep, there's this matrix, LAB, which constitutes the spin part. Transformation. And the spin part of the transformation acts on the indices. Right, so again, I said that this index A could be a spinor index, it could be a vector index. Okay, I'm not specifying, but it's clear that this guy acts on these indices and summation. So the spin part of the transformation acts on the indices of the field and is encoded in this matrix LAB of G. This part is actually dependent on the specific representation that the field belongs to. So if it's a spinor, if it's a vector, this guy will change. Okay, so this acts on the indices and is representation and so with different representations of the field, this set of indices will change. So what we would like to do is realize this transformation law in the Fox space of the CFT filter space. And to do this, it will be helpful to think of fields as operators. In which case, the transformation law looks as follows. Thinking of fields as operators. Transformation law 2 becomes following. Find a tilde of x is u of p dagger phi a of x u of t, and this must equal to the right hand side here L can be d of t phi p of g inverse x. Okay, again, I want to unpack this. Let's call this 3. Right. So the idea of representation here is I have a group. The group consists of some set of group elements, some group representation, some group operation. Right. And representation theory maps the group element to some element of some algebra. Okay, some matrix realization of this. We call this thing U. Under the transformation G, field phi a followed as an operator must go to U dagger phi a G. So U. Okay. But we said earlier here that this field phi is going to LAB phi B. That's that. Yeah. So those two must be the same. Those two must be the same, and therefore. Now, if this is to be true, it needs to be consistent with the transformation problem, operating transformation problems. So let's check that the group operation of operating transformation is preserved by take this, calculate Q dagger of G1, G2, phi A of X, U of G1, G2. Okay. So the group operation says that G1, G2 is G1 times G2. Right. And then the representation, this is a faithful representation, if U of G1, G2 is U of G1, U of G2. Okay. So in here, this product is a product taking place in the group. U of G1, U of G2 is a normal matrix multiplication in the linear algebra that I'm realizing these matrices on. So that's normal matrix multiplication, right? And if the group operation is preserved under this map, then U of G1, G2 is U of G1, U of G2. Okay. So this is equal to, well, if U of G1, G2 is U of G1, U of G2, then U dagger is U dagger of G2, U dagger of G1 times phi A of X, U of G1, U of G2. And then I can bracket this. Okay. And I know that what's sitting in here, U of G2, U dagger of G2, what's sitting in here must be L A B of G1 phi B of G1 inverse X, and on the outside is U of G2. Okay. This is commuting with these two because they live in a different space, so I'm going to pick them up. That's L A B G1 U of G2 dagger phi B of G1 inverse X U of G2. And this here is just L, let's say B C of G2 phi C of G2 inverse G1 inverse X. Right. And this is as expected if the transformation property, if the transformation law T preserves the property. However, I would like you to notice something, which is that the orbital part says operate with G1 first as G1 inverse and then G2. Whereas the spin part says operate with G2 first on phi and then G1. So notice the order here. We're going to come back to this in a little bit. Okay. So the transformation is in the reverse order on the coordinates as the T's. Now, that's all well and good if you want to establish, these gross properties like the transformation of the field. But what we've been used to doing is instead of working with the elements itself, we work with infinitesimal elements. Okay. And then we can always exponentiate to read off the action of the full group. So let's do that and ask what we can learn. So let's consider the infinitesimal. Under which x mu tilde, which we were saying was p x mu, can be written as x mu plus some psi mu. The point is that this guy here will be a killing vector. Or in the case of conformal transformation, a conformal killing vector. Then the spin part of the transformation can be put into the following form. L A B of L A B of G exponential of I over 2 omega mu times some generator sigma mu. And these generators are just matrices that are obey the correct linear the algebra and are representation dependent. So these are some set of generators of matrices that obey the correct algebra. Are representation these are matrices. I'm exponentiating these matrices. So by Taylor expansion, this is just the matrix itself. It also carries a B index. So note that. I'll make those A B indices like that. The total transformations in the formal killing vector. For the Lorentz, for example, we know because we solved the killing vector equation that this time u is a constant translation vector AB plus omega mu, this omega mu times x nu. And some examples of the associated generator signal mu. mu nu is equal to 0 for scalars. Mu nu is equal to quarter of commutator of gamma nu, where the gammas here are a set of gamma matrices. Means that this is for a spinner. And sigma mu is equal to, or rather, sigma mu B is equal to I delta mu A delta mu B minus delta mu B delta mu A. So just conjugate deltas for a vector field. Scalar fields describe fermions, vector fields describe things like gauge fields. So this is what the spin generators look like in those cases. But what is our transformation law? Here. No, sorry. This guy. No, sorry. This one. Look like in terms of this generator. In terms of generators, by a tilde is delta A B plus I over 2 omega mu omega mu downstairs sigma mu upstairs, and sigma carries all the A and B indices. So to first order, that's what this matrix LAB looks like. But then it multiplies by B of G inverse X. Okay. And so G of X takes X to X plus psi. We know what this psi is for the Lorentz. So the inverse of X is X minus A mu, X mu minus A mu minus omega mu nu. X mu. Okay. The minus signs come from that minus sign. Now let's calculate the difference delta on A of x phi tilde A of x minus phi A of x. And the reason we want to do this is because we want to be able to read off the action of the generators of series. The first point to note is that phi A tilde of x and phi A of x are not evaluated at the same point in space-time. Right? Even though phi A tilde is a function of x, it's really evaluated at g inverse x, and that's a different point in space-time. Okay, so these fields are evaluated at different space-time. However, they're evaluated at the same point in the Lie algebra. So let me just make a reference here to what we did in the differential calculus. A Lie group, every Lie group is a continuous group. It's continuous because its parameter, the parameters of the transformations, right, that are realized in the Lie group are continuous parameters, like U1, right? To each Lie group, I can associate a group manifold, right? In the same sense that we've been talking about in the differential geometry. It's a smooth space on differential problems. The Lie algebra is itself a manifold. That manifold is the tangent space to the Lie group manifold at the origin. So I have some continuous manifold, find the origin of the manifold, pick that point, construct the tangent space to that point. The Lie algebra is a set of things that live in that tangent space. Okay. And this is why we like the algebra, because we can do linear algebra with things that live in that tangent space. Okay. Now, even though these two fields are evaluated at different points in space-time, they're evaluated at the same point on the Lie algebra. So they're evaluated at the same point in the tangent space to the Lie group manifold. Okay, keep that in mind. Now, the reason I want to bring that up is because I can now calculate what delta phi is. Substitute back for this guy into here, and I will find that it's minus a mu d mu phi a of x, because I'm making an expansion about x mu, right? This minus sign comes from here, the derivative comes from the first term of the Taylor expansion, right? I make the Taylor expansion about x mu with x mu minus this guy minus omega mu nu delta a d x mu d mu minus I over 2 sigma mu nu a b acting on b of s. The only part that is representation dependent is this split matrix. Yeah. All the representation dependence is sitting in here. Okay. But this guy must be I times the commutator of A dot P, P being the momentum generator, minus half omega mu nu m mu. This guy is a generator of Lorentz boosts and rotations. So this is the form that we're just familiar with already from what we studied about the Lorentz transformations previously. Phi A. And the reason why the commutator here is because the protocol operates. And from here, we can then just read off what the actual generators of the fields are. So, for example, if I ask what is the action of the momentum generators on the fields phi A, that's P mu phi A of x. When I compare this guy to this guy, this is A dot P is A mu P mu. Right? So that's just minus, pi d mu on phi A of x. And again, we can identify the action of P mu as the action of the okay. Similarly for the mu as well. So what about, so far we've talked about the Poincare subgroup of the form. Right? What about the Western form? Now, to answer this question, we're going to do something similar to what you may have seen in the analysis paper. Not but okay. If you're doing if you're doing quantum field theory, at some point you will do a similar trick to what we're going to do now. I mean, it's called Wigner's method. Wigner's method involves writing down irreducible representations of the Lorentz. Okay, because if you do quantum field theory, you do quantum field theory in flat space, and the relevant group that you're interested in is the group of Lorentz transformations and maybe Poincare transformations, but essentially Lorentz transformations. So what you want to know is how do the fields in your theory transform under these Lorentz transformations? And they transform in various irreducible representations of the Lorentz group. So in order to write down what the irreducible representation is of the Lorentz group was, what Wigner did was come up with what's called Wigner's little group analysis of the Lorentz. The little group analysis, what you do is you make a particular boost to a particular inertial frame that makes your life simpler, right? You know that the physics is boost invariant, it's Lorentz invariant, and that allows you to cast things in as simple as possible, in a simpler way as possible, in order to determine the irreducible representation of the Lorentz. Okay. So what we're going to do is something similar, except because we're talking about conformal transformations. Essentially, we need to only specify the transformation properties of fields, not everywhere in space-time, but just at the origin. And that's because I can translate every point in space-time to the origin, work out the transformation properties, and then translate them. Okay? So we are going to follow similar logic to Wigner's little group analysis. And specify the transformation properties. of A as 0. So this is because I can take any field and translate it to the origin. Once there, these fields are related by conformal transformation that leave the origin invariant. And what we will do is show that we won't lose any information by variance. Okay. So in order to translate a field to the origin, I do what I've done with, I do what we do in going between, let's say, Schrodinger picture and the Heisenberg picture. So there, I have in the Schrodinger picture, my operators are time independent, right? And in the Heisenberg picture, they're time dependent, and I relate to by an exponential of the Hamiltonian. Okay, so here, phi A is e to the I x. Like x p phi A 0 minus phi x. This kind of makes sense, right? The Hamiltonian affects translations in time. The momentum generator affects translations in space. So that's exactly the same structure as with translating things in time, with the Schrodinger picture to the time dependent Heisenberg picture. Here I go from the field specified at the origin to the field specified at some point that's translated to the origin. You affect this by exponentials of the momentum generator. Then for fields located at the origin, Lorentz transformations act as follows. For fields at the origin, Lorentz transformations as M union by at naught is sigma union A B phi B. I think let me stop here because the next calculation is a little bit long. I don't want to I don't want to stretch it over two lectures. So I'll do the next calculation next lecture, which is Wednesday, right? On holidays. Good. Right, so what I'll do next time is I'll show you that split actually, I can make one comment here, which is that the action of the Lorentz transformation only contains the split part of the transformation. Right? This is a direct consequence of the fact that Lorentz transformations leave the origin invariant. So only the split part is present. My point here is that Lorentz transformations act on these fields specified at origin in this way. There is no orbital part here. It's just a split part of the transformation. This is because Lorentz transformations leave the origin invariant. But of course, we should ask, have we lost any information about the orbital part by specifying just the field at the origin? And I'll show you in the next lecture that we have. That is to say, once I know how the field at the origin transforms, I know how the field transforms in any okay.